Imagine deploying a piece of code, right?
Hmm.
And a single decimal point is off by just 1 millimeter.
Yeah.
And that tiny error costs your company $10 million in completely wasted cloud compute.
Just gone. Instantly.
Right. I mean, for software engineers building deterministic systems, that sounds completely absurd. You write a function, you pass an argument, you get a reliable return value.
Yeah, that's the dream anyway.
Exactly. But if you're listening to this right now, maybe you're a developer staring at a terminal window waiting for a build to finish, you probably know that the world of large language model training plays by a completely different set of rules.
Oh, absolutely. It is a wildly different beast.
Tonight, we are going deep into the hidden engine of AI training. We're looking at a great stack of sources covering learning rate schedules.
It's a fascinating topic.
It really is. We're specifically unpacking why the pace of AI training is considered this incredibly fragile art form. It's late, the studio is quiet, so let's just get right into it.
Sounds good to me. You know, that transition from deterministic software to, well, probabilistic AI training, it's really jarring for a lot of engineers.
Yes, I can imagine. You're giving up a lot of control.
Exactly. You are no longer just compiling code. You're navigating this highly dynamic, chaotic system. And the single mechanism that keeps this massive computational effort from literally flying apart is the learning rate.
The master dial.
The master dial. In the literature, it's universally recognized as the single most impactful hyperparameter in AI training. Bar none.
Wow.
Yeah, I mean, before you even worry about the nuances of your transformer architecture and way before you look at the quality of your data set, you have to get the specific dial right.
Let's see, I'm used to dials where turning them up to a 10 just means the system runs faster.
Right, like overclocking a CPU.
Exactly. If we want the model to learn, why doesn't a maxed out learning rate just equal a faster training time? Why is this specific dial considered so, dangerous?
Well, it comes down to what the learning rate actually represents mathematically. During a training loop, the model makes a prediction on the data, right?
Right. It guesses the next word.
Yep. And then it calculates how wrong that prediction is, which we call the loss, and then updates its billions of internal weights to be slightly less wrong the next time.
Makes sense.
So the learning rate doesn't dictate the speed of the hardware. It dictates the actual physical size of the mathematical update applied to those weights. It's the step size the model takes through the data.
The step size. Okay, let's visualize that. Picture navigating a dark, totally jagged mountain range in the pitch black.
I like this. Okay.
Your goal is to find the absolute lowest point in the valley, right?
Yeah.
Because that represents the lowest possible error rate for the model.
Exactly. Zero loss is the bottom of the valley.
So you have a mathematical compass, the gradient, that tells you the general downward slope. But you still have to decide how big of a step to take in that direction.
And that's your learning rate.
Right. So if your step size, your learning rate, is just massive, you might try to step completely over a ridge. You end up vaulting right off a cliff.
Yep. The math completely breaks. You get overflow errors and the model diverges.
And divergence is bad.
Divergence is catastrophic. I mean,
Yeah.
in traditional software engineering, if an application crashes due to, say, a memory leak, what do?
You restart the service. It
Well-
takes 30 seconds.
Right. And your monitoring tools log the event, no big deal. But in distributed AI training, a divergence might happen 2 weeks into a continuous run on a cluster of 10,000 GPUs.
Oh, wow.
Yeah. When the weights explode into useless, undefined numbers, the run is just dead. You vaulted off the cliff, and there is no simple sectoral Z that gets back the compute time you just burned.
Which makes me think, as an engineer who is, frankly, terrified of that cliff, I would just hard code the system to take microscopic steps.
Just inch your way down the mountain.
Exactly. Move 1 millimeter at a time. The math stays perfectly stable, no divergence, no cliffs. What is the penalty for playing it safe like that?
The penalty is that you never reach the bottom of the valley before you run out of time and budget.
Ah, right. The cloud bill.
The cloud bill is brutal. Compute is incredibly expensive. We are talking about thousands of dollars an hour to rent these massive GPU clusters.
So going slow isn't free.
Not at all. If you take microscopic steps, your model is essentially spinning its wheels. It's updating its weights, it's processing terabytes of data, but it's making such tiny mathematical adjustments that it isn't actually learning the underlying patterns.
That sounds incredibly frustrating.
It is a massive financial hemorrhage. You're burning cloud credits to learn, essentially, Nothing. So you are forced to find the sweet spot between vaulting off the cliff and crawling at a snail's pace.
Yeah, looking at our sources here, that sweet spot isn't a static number, is it? We can't just find a magical medium setting on the dial, lock it in, and go grab a coffee.
I wish. No, it doesn't work that way.
The optimal step size depends heavily on the model size, the batch size of the data, and crucially, the specific phase of the training run.
Yes. The phase of training is huge.
We have to constantly adjust the dial while the massive engine is running. Which brings up a really interesting architectural problem, starting with the very first second the system boots up.
The warm-up phase.
Right. The sources show that every major training run begins with this warm-up phase, consisting of 500 to 2,000 steps at an incredibly low learning rate.
Very low. Barely moving.
But wait, from a pure engineering standpoint, this feels really counterintuitive. Code usually executes identically on the first millisecond as it does on the millionth.
Usually, yeah.
These models are just doing matrix multiplication. Why do mathematical equations need a gentle warm-up to, calibrate? They aren't physical gears that need to be oiled, right?
That's a brilliant question. And the answer really lies in the state of the system at step 0.
Step 0, okay.
When you initialize a fresh neural network, its internal weights, those billions of parameters that dictate how information flows, they are effectively randomized.
So it's just pure noise.
The model is a blank slate of pure noise. It has absolutely zero underlying logic or structure.
So if we hit a completely randomized system with massive, aggressive mathematical updates right out of the gate,
You permanently scramble whatever nascent logic it was trying to form.
oh, wow.
Let's look at the specific internal components mentioned in the sources. Take the atom optimizer, for example.
That's the algorithm that actually applies the updates to the weights, right?
Exactly. And it relies heavily on what we call moment estimates. It tracks the moving average of past gradients to, smooth out future steps.
So it essentially builds a historical trajectory to keep the model moving in a stable direction.
Right. But at step 0,
There is no history.
there is zero history. So if your learning rate is set to maximum on step 1, Atom sees a massive error because the randomized model naturally outputs total garbage.
Right. It guessed the word completely wrong.
Exactly. And Atom tries to forcefully rewrite the weights all at once to fix it without any historical variance to temper that update. The math just explodes.
That makes total sense. And the sources mention LayerNorm too, right?
Yeah.
Yes, LayerNorm is another big one. It stabilizes the data flowing between different layers of the network. It needs to calculate the mean and variance of the data passing through it.
And on the first few steps, those statistics must just fluctuate wildly.
Wildly. And the attention patterns, too, the mechanisms the model uses to decide which words in a prompt relate to each other. They're just pointing blindly in random directions.
So the necessity of the warm-up phase is incredibly clear. It isn't that the math physically needs heat. It's that the system needs to establish a baseline of sanity.
A baseline of sanity is a great way to put it.
Those first 500 to 2,000 steps at a microscopic learning rate allow LayerNorm to stabilize its statistics over a few batches of data, right?
Yeah. And it allows the atom optimizer to gather a little bit of historical momentum so it isn't flying completely blind.
It gives the attention patterns just enough time to orient themselves to basic sentence structures. We're gently guiding the system out of total random chaos into a state where it can actually survive a large mathematical update.
Spot on. And only after that foundational stability is established can you safely throttle the engine up to its peak learning rate.
So now the model is capable of absorbing massive amounts of information quickly.
Yes. But of course, you can't stay at top speed forever.
Right, the cliff is still out there.
Exactly. As you process more data and get closer to the optimal solution deeper into our mountain valley, you need a reliable way to hit the brakes.
And the sources point to a very specific industry-standard technique for hitting the brakes. They call it cosine annealing.
Cosine annealing, yeah, it's everywhere.
It's not a straight line sloping downward, it's a specific mathematical curve. So how exactly does the shape of a cosine wave solve the problem of slowing the model down without ruining the training run?
Well, cosine annealing solves a really complex optimization problem by breaking the deceleration down into 3 distinct phases. You have lingering, dropping, and settling.
Okay, lingering, dropping, settling.
Right. The first phase dictates that the learning rate lingers near its absolute peak for a significant portion of the training run before it really starts to decay.
If I'm picturing this right, it is almost like landing a spacecraft.
Okay, I'm with you.
That lingering phase is like cruising at top speed in high orbit. You're covering massive amounts of distance and surveying the entire planet below.
Yes, exactly. In machine learning terms, keeping the learning rate high prioritizes what is called exploration.
Exploration.
Yeah. If the model steps into a shallow suboptimal valley, a bad local minimum, that high energy and massive step size allows it to literally bounce out of that trap and keep exploring the broader mathematical landscape.
That is the perfect way to frame exploration. You don't want the model committing to the first half-decent solution it finds. You want it to find the absolute best valley.
Right. But eventually, you've surveyed the landscape, and the model has found the general region of the true optimal valley. This triggers the second phase of the cosine curve.
Where the learning rate drops rapidly.
Yes, it plunges.
So our spacecraft executes a rapid deceleration burn to break through the atmosphere.
And mathematically, this rapid plunge shifts the model from exploration to exploitation.
Exploitation. Okay, so because the step size shrinks drastically, the model can no longer bounce out of valleys.
Exactly. It's forced to stop sweeping past the data and start committing to the specific, nuanced features of the information it is currently processing. It starts exploiting the local area to find the lowest possible error rate.
And finally, we hit the third phase. The curve doesn't just smash into zero, does it?
No, definitely not.
It settles incredibly gently, flattening out as it approaches the end of the run. So the spacecraft uses its thrusters to feather down for a perfectly gentle touchdown.
This is the fine convergence phase. If your learning rate remained even slightly too high at the very end of training, the model would violently bounce back and forth across the absolute bottom of the valley.
Constantly overshooting the exact lowest point.
Exactly. That gentle, feathered tail of the cosine curve allows the weights to settle into their final configuration with microscopic precision.
So we've got the warm-up, the high-speed orbital exploration, the rapid atmospheric drop into exploitation, and the feathered touchdown. It really is a brilliant orchestration of math.
It's beautiful when it works.
But everything we have discussed so far assumes a neat, contained environment. As an engineer, the reality of modern AI is massive horizontal scaling.
Oh yeah. A single GPU won't cut it anymore.
Right. We are not running this cosine curve on a single machine. We are chopping this workload up and distributing it across thousands of GPUs simultaneously. How does this incredibly delicate curve survive that kind of distributed infrastructure?
It survives through the application of the linear scaling rule.
The linear scaling rule.
Yeah, it governs how we adjust our master dial when we change our batch size. Because to coordinate thousands of GPUs, you can't feed the cluster one document at a time. The network synchronization overhead would just bring the whole system to a halt.
Right. The servers would spend more time talking to each other than actually doing math.
Exactly. So instead, you increase your batch size. You send micro batches of data to every single GPU. They all calculate their local gradients independently, and then they perform a massive network operation and all reduce to average those gradients together and update the master weights.
So instead of the model looking at 10 examples before taking a step, our massive cluster allows it to look at 10,000 examples simultaneously before taking a step.
Right.
But if the model's processing 1,000 times more data per step, taking the same tiny step size seems incredibly inefficient.
It is entirely inefficient, which is why the linear scaling rule dictates that you must scale your learning rate proportionally with your batch size.
Okay, so if you double the amount of data in your batch, you double your learning rate.
Precisely, and the logic is rooted in the signal-to-noise ratio. When you calculate a gradient on a tiny batch of data, that compass reading is inherently noisy.
Because it might be skewed by a few weird documents in that specific batch.
Exactly. So you take a small step because your confidence is low.
But when we average the gradients across 10,000 documents from thousands of GPUs, the weird outliers cancel each other out.
Yes, you get a perfectly clear, highly confident compass reading pointing straight down the valley.
And because the reading is so accurate, we can safely take a massive step, a much higher learning rate, without fear of vaulting off a cliff.
You've got it. The linear scaling rule keeps the mathematical progress perfectly consistent as you scale out your hardware.
Okay, I have to push back here.
Go for it.
If it is just a linear rule, that implies an infinite runway. If I spin up a monster cluster of 100,000 H100 GPUs and push my batch size to 1 billion documents, I can't just multiply my learning rate by 10 million. There has to be a breaking point where the math snaps.
You are absolutely right. There is a breaking point, and the sources identify it as the critical batch size.
The critical batch size, okay.
Your intuition is completely correct. You cannot scale to infinity. When you increase your batch size, you are reducing the variance, the noise, in your gradient estimate. But eventually, you hit a mathematical ceiling.
At a certain point, calculating the gradient across 10 million data points doesn't actually give you a cleaner, more accurate compass reading than calculating it across 1 million data points.
Because you've already captured all the inherent variance in the data set.
The signal is completely maxed out.
Exactly that. The noise has essentially zeroed out. So if you try to blindly follow the linear scaling rule past that critical batch size limit, if you keep doubling your learning rate just because you added more servers to your cluster, the compass isn't getting any more accurate, but your steps are getting dangerously huge.
And the stability of the training run collapses, and your model diverges.
Right off the cliff. The critical batch size is a hard mathematical limit imposed by the data itself. It's completely independent of how much physical hardware you throw at the problem. Scaling infrastructure requires scaling the math in absolute lockstep, but knowing when to stop scaling is just as vital.
That perfectly bridges the gap between the infrastructure and the math. But we've really only solved half the scaling problem. Tuning the batch size is tricky, sure, but what about scaling the physical size of the neural network itself?
Yeah. That's the real challenge.
The sources discuss frontier labs training trillion parameter models. And if you think about the workflow we just established to get a successful run, we have to perfectly tune the warm-up steps, precisely shape the cosine glide path, and strictly abide by the critical batch size limits.
It's a lot of variables.
It is. And if you try to find all those optimal settings through trial and error on a trillion parameter behemoth, the compute costs for the failed experiments alone would bankrupt a tech giant.
Oh, easily. Tens of millions of dollars just up in smoke.
So how do the frontier labs actually do it? How do they avoid burning cash guessing the right learning rate schedule?
They avoid guessing by utilizing a framework known as MUP. That stands for Maximal Update Parameterization, and they use it alongside small-scale proxy models.
MUP and proxies.
Yeah. In the world of frontier AI development, MUP is arguably the most important operational methodology in existence. It allows researchers to completely decouple hyperparameter tuning from the final massive training run.
To put MUP into an engineering perspective, I look at it like a wind tunnel for a commercial jet. But we need to go a step further than just the physical shape.
Okay, I like wind tunnels. Let's hear it.
If an aerospace company wants to build a massive, revolutionary new 747, they don't build a full-size prototype out of expensive aerospace titanium just to see if the wings generate lift.
Right, because if the math is wrong, they crash a billion-dollar asset. It's too risky.
Exactly. Instead, they build a perfect 5-foot miniature. But here is the catch: air doesn't naturally flow over a 5-foot miniature the exact same way it flows over a 200-foot jet.
The physics change at scale.
Right. So aerodynamicists use a mathematical constant called the Reynolds number to adjust the wind speed and pressure in the tunnel. It scales the physics so the miniature behaves identically to the massive jet. MUP is basically the AI equivalent of the Reynolds number.
That is a phenomenal analogy. Because in standard neural network parameterization, if you just take a small model and make it drastically wider, adding billions of parameters, the mathematical energy, the activations flowing through the layers, tends to blow up or vanish.
The physics of the small model do not naturally translate to the physics of the large model.
Exactly. So the optimal learning rate you found for the small model will cause the large model to immediately diverge.
The wings rip off the giant plane even though the miniature flew perfectly in the tunnel.
Precisely. So MUP changes how the weights are initialized and how the learning rate is applied. Specifically, it scales them by a factor related to the width of the network.
Oh, that's clever.
Very. By fundamentally rewiring the underlying parameterization, MUP ensures that the flow of mathematical energy remains constant regardless of how wide the network gets. It forces feature learning to become independent of model size.
So the workflow completely changes. You build a tiny 100 million parameter proxy model. Because it is so small, you could afford to run thousands of cheap experiments on it.
You can iterate all day.
You dial in the exact aerodynamics, the perfect warm-up length, the exact peak learning rate, the ideal cosine curve. And because you are using the MUP framework, you can take those exact optimized hyperparameter curves and transfer them directly to a massive trillion parameter model.
With absolute mathematical confidence that they will work on the very first try.
That blows my mind. For a software engineer managing cloud budgets, the value of MUP is just staggering.
We are talking about eliminating tens of millions of dollars in wasted compute that would otherwise be spent blindly tuning hyperparameters at scale.
It turns a trial-and-error financial disaster into a highly predictable, systematic engineering process.
It's the silent framework that allows the industry to push the boundaries of scale without going completely bankrupt.
It really all comes back to managing the chaos of probabilistic systems. When we look at the whole journey of a training run we've mapped out tonight, it is a masterclass in control.
It really is.
We started with the absolute danger of the master dial, the learning rate, knowing that stepping too far causes a catastrophic divergence, while stepping too cautiously wastes fortunes in compute time.
Yep. And then we looked at the necessity of the 500 to 2,000 step warmup, giving chaotic internal mechanisms like atom optimizers and LayerNorm statistics the time they need to establish a baseline of sanity.
We charted the cosine annealing glide path, perfectly balancing the high-speed exploration of the data landscape with the rapid drop into exploitation, and finally, the feathered convergence at the absolute minimum error rate.
We navigated the network bottlenecks of distributed training using the linear scaling rule, increasing our step size in lockstep with our batch size.
While being incredibly careful not to break through the mathematical ceiling of the critical batch size.
Right. And finally, we explored how frontier labs use MUP as a mathematical wind tunnel, scaling the initialization physics so they can tune everything for pennies on proxy models before launching trillion-parameter behemoths.
It is a remarkable sequence of solutions, but it is crucial to remember what this massive, highly tuned engine actually is at the end of this process. Our sources are quick to point out that after all of this careful pre-training, after writing the cosine curve perfectly, the resulting model is incredibly capable, but it is purely a text predictor.
That's a great point. It just knows how to statistically complete a sentence based on the data it ingested.
Right. It doesn't know how to act as an assistant. It doesn't know how to follow formatting instructions. And it certainly doesn't know how to answer questions conversationally.
The next stage in the pipeline is supervised fine-tuning, or SFT. That is where we take the raw, powerful engine we just built and carefully teach it how to actually interact with a human user.
We provide it with high-quality, human-curated examples of instructions and responses.
But without the massive foundational pre-training mechanics we unpacked today, there is no underlying intelligence to fine-tune.
Which leaves me with a lingering thought. Something I want you, the listener, to mull over the next time you are architecting a complex system or dealing with the constraints of deterministic code.
Okay, let's hear it.
The learning rate literally dictates the exact trajectory the model takes as it traverses the vast landscape of all human knowledge. Right? We've spent this entire deep dive talking about the schedule as a strict mathematical necessity. It's a way to avoid crashing the hardware or wasting money.
Right. An engineering constraint.
But consider the psychological implications of that math. Does the exact shape of that decay curve fundamentally alter the model's ultimate worldview?
Oh, that's interesting.
Right. If we tweak the cosine wave, if we force the model to linger at the highest peak of exploration just a little bit longer before decelerating, or if we drop the rate drastically early to force exploitation, do we inadvertently change what the model values? Does a fast, aggressive schedule create an AI that easily grasps broad concepts but entirely misses nuance? While a long, slow, feathered decay creates a model obsessively fixated on trivial details. We tune these master dials entirely for training speed and cluster stability, but in doing so, are we unknowingly shaping the very personality and cognitive style of the AI long before fine-tuning even begins?
That is wild to think about.
Something to think about while you write your next line of code. Until next time.